So this is going to be our lesson video for section 17.1. I'm actually going to break it up into two videos because the section is really long. So keep in mind that if you want to get all my videos in one place, you can just subscribe to my channel. Just a fun fact, my husband subscribed to my channel because he's so awesome. So you know, one day when I'm like a YouTube sensation, have like 3 million subscribers, my husband will be one of the first ones. And he also liked one of my videos, thanks. So anyway, enough about how great my husband is. Let's go ahead and start this section. So, section 17.1, we're going to jump into thermochemistry. So first we got to talk about some definitions. So thermodynamics is the study of energy and its transformation. So where is it going? Is it changing into a different form of energy? That type thing. Energy is the ability to do work or transfer heat. In chemistry, we normally focus more on the heat, but we do focus on the work a little bit because reactions can do work, like a dynamite explosion moving large chunks of rock to another location. That's an example of doing work. Work is the energy used to cause an object with a mass to move against a force. You probably learned that in physical science or physics. And then heat is the energy used to cause the temperature of an object to increase. Alright, so again, these are just some definitions that we need to know for this section. So kinetic energy, you probably learned this in physics and physical science, is the energy of motion, and the formula is Ke equals 1/2 mv squared. Now usually in chemistry, V is volume, but in this case it is velocity. And the important thing is, in chemistry, a lot of times we use mass as grams, but it has to be kilograms, and velocity has to be meters per second. And the potential energy is the energy that an object has due to its position. And so potential energy is mass times acceleration due to gravity times height. And again, mass must be in kilograms, height must be in meters, and your g, or acceleration due to gravity, if you've forgotten, is the 9.8 meters per second squared. So what that means is as speed increases, your kinetic energy increases. As height increases, your potential energy increases. So if you watch the roller coaster, high, lots of potential energy. When it's moving faster, you'll see that kinetic energy shoot up. So they're always kind of going back and forth, back and forth. Like if you think about when you learn about the pendulum in physical science or physics. So one type of energy we're also going to talk about is electrostatic potential energy, because of course that's based on charged particles, which is what chemistry is all about. So it arises from the interactions between charged particles. So your electrostatic potential energy is kappa times Q1 times Q2 over D. So what do all these things mean? Well, K is your kappa, is a constant, 8.99 times 10 to the 9 joules times meters per coulomb squared. Okay, so a lot of units going on there. You know how it is in chemistry. When a constant has a lot of units, it's just so they can cancel out with some of the other variables. Your Q1 and Q2 are a multiple of 1.6 times 10 to the negative 10 coulombs. That is the charge on an electron. So what charge does it have? Like if it's a positive 2 charge, it would be 2 times this. If it's a negative 3 charge, it would be 3 times this, but of course then it would be negative. And then D is your distance in meters. So since distance is on bottom, that means as distance increases, your electrostatic potential energy decreases. Because of course, the more energy, we want them to be close together. They need to be close. So if Q1 and Q2 have the same charge, so say they're both positive or both negative, the energy is positive and the charge is repelled. So if all the numbers you plug into the formula I just showed you are positive, energy will be positive. And remember, we talked about energy is most favorable when it's 0 or when it's losing energy, so it's negative. And that's exactly what happens if Q1 and Q2 have opposite charges. If one's positive and one's negative, your overall answer will be negative, and that's favorable, so those charges attract, whereas a positive energy is unfavorable, so they repel one another. And then, of course, our energy decreases with increasing distance. Remember, when the charges want to attract each other, we want them to be close enough to get near each other. So, chemical energy is due to the potential energy stored in the arrangement of atoms. So, thermal energy is the energy a substance possesses due to its temperature, and chemical energy and thermal energy are both important in chemical reactions. So again, this is just more definitions. When we first get into thermochemistry, we have a bunch of vocabulary to sort out. Okay, so we've got chemical energy, which is based on the bonding and the arrangement of the atoms, and thermal energy is due to temperature. So the higher the temperature, the more thermal energy you have. And then both of them are important on whether something is endothermic or exothermic in a chemical reaction. So what are some units that we're going to talk about for energy? Because you saw joules, you saw coulombs, things like that. So a calorie is the quantity of heat that raises the temperature of 1 gram of pure water 1 degree Celsius. However, we don't really use calories. That is something we use in America, and as many of you have heard me say multiple times, the units we use in America are not the smartest unit choice. The SI unit for energy is the joule. It's represented by a capital J, and a joule just comes from the formula that we plug into, like the mgh for potential energy, or the 1/2 mv squared for kinetic energy. It's a kilogram times meter squared per second squared. So instead of having to write all that every time, we just write joule for J. A calorie is another unit of energy. Again, lots of other countries don't use this, and that's smart because we don't even really use calories and we live in America. So how do we get between the two? 1 calorie equals 4.184 joules. So make sure you know that conversion. Now there is a difference in a lowercase c calorie and the capital C calories that you see on your food. So a capital C calorie is a nutritional calorie, and it's actually a kilocalorie. So 1 calorie on your food that has the capital C is really 1,000 lowercase c calories. All right, so just be aware that a nutritional calorie and a calorie we use in science are two different things. The nutritional calorie is actually 1,000 times because it's a kilocalorie. So let's look at how to make these conversions. All right, so we'll look at the first one together. So it says we have 444 calories to joules. So I start with my 444 calories. And golden rule says, of course, calories has to go on bottom. So I think about my conversion factor. 1 calorie equals 4.184 joules. Those calories cancel, and so then when I multiply, I got 1,857.7 joules. Okay, so super easy conversion. You just got to follow your golden rule. Whatever unit you start with goes on bottom. So y'all try this one and then pause, check your answer, and we'll go over it right now. So 850 joules. So what we're starting with, we're going to calories. So of course, golden rule says I need to put joules on bottom. And this time it's the 4.184 joules equals 1 calorie. So those joules cancel, and in this case I divide. And when I divided, I got 203.3, and the unit I'm left with is calories. All right, so that's how you go between joules and calories. Just make sure you know that, because every now and then I'll ask you for units and calories, but most of the time you got to get to joules. So next, let's talk about work and heat. So work is the energy used to move an object against a force. We already discussed that. And the formula that you may recognize from physical science and physics is work equals force times distance. Heat is energy transferred from a hotter object to a colder one. So the thing that people get confused about is cold is nothing. Cold is actually just the absence of heat. Heat is a form of energy that goes from the hotter object towards the colder object because it wants to dissipate and spread out, just kind of like diffusion. Go from high concentration to low concentration. Heat does the same thing. So let's look at how to do some calculations with energy. So it says a bowler lifts a 5.4 kilogram or 12-pound bowling ball from ground level to a height of 1.6 meters or 5.2 feet, and then drops the ball back to the ground. What happens to the potential energy of the bowling ball as it's raised from the ground? Well, if you remember on the previous slide, I told you that potential energy is mass times acceleration due to gravity times height. So as height increases, your potential energy also increases. All right, then it says, what quantity of work in joules is used to raise the ball? Okay, well, work, we just said, is force times distance. Well, they gave me distance. I'm not going to use the feet, though, obviously. Again, that's what we use in America, and it doesn't make any sense. So we're going to use the 1.6 meters, but they didn't give me the force. So I gave you the hint here. Force is mass times acceleration. In this case, our acceleration is acceleration due to gravity, which I told you is the 9.8 meters per second squared. So since I know that, again, not using American units, since I know the kilograms as my mass, I can multiply by the gravity. So my force is my mass, which is my 5.4 kilograms, times my acceleration due to gravity, which is 9.8 meters per second squared. So once I multiply that, I got 52.9. And if you remember from physical science or physics, your unit for force is newtons. It's just a kilogram times meter per second squared. And so now I can plug my force in here. So my work is my force, 52.9 newtons, times my distance, which is 1.6 meters. And so once I multiplied, I got 84.6 joules. Because once we multiply by another meter, you see how newtons was kilogram times meter per second squared? A joule is a kilogram times meter squared per second squared. So once we multiply by that other meter, that's what turns a newton into a joule. All right, so hopefully that wasn't too bad, just a little bit of math going on. So let's look at this one. So it says, after the ball is dropped, it gains kinetic energy. If we assume that all the work done in part B has been converted to kinetic energy by the time the ball strikes the ground, what is the speed of the ball at the instant just before it hits the ground? And then again, I gave you the note that gravity is, of course, 9.8 meters per second squared. All right, so here we are looking for speed. We are assuming that all the potential energy was converted to kinetic energy. So that means it's going to be what we just got in our previous answer. So we got 84.6 joules. So we need to rearrange our kinetic energy formula, which is 1/2 mv squared. We need to solve for velocity. So how do we get rid of the half? Well, you can multiply both sides by 2. How do we get rid of the mass? You can divide both sides by m. How do we get rid of the squared? You can square root both sides. So I know this is a whole bunch of stuff, but y'all should know how to do basic algebra. So that gives us V equals square root of 2 times the kinetic energy over the mass. And so then we just plug in. So 2 times my kinetic energy, which is 84.6 joules, over my mass, which is, I think it was 5.4 kilograms, but I don't remember. All right, 5.4 kilograms. So once I divide and square root and everything, I end up with 5.6, and my unit is meters per second. Okay, you know that for 2 reasons. One, the unit for velocity is just meters per second. But 2, if you remember, a joule is a kilogram, which that's going to cancel with this kilogram, times meters squared per second squared. So if you square root a meter squared and second squared, you get meters per second. Okay, so either way, you'll get the right unit. All right, so hopefully that wasn't too bad. Important thing to remember though is, like I said, mass has to be in kilograms and velocity has to be in meters per second. If I give it to you in something else, you'll have to convert it. So y'all try these. I will tell you, I did give you the hint about what 1 AMU equals for this one, so that you can get to grams and then get to kilograms. And so y'all try these real quick. Just pause it, try them, and then we'll do it together right now. So it says, what is the kinetic energy in joules of an argon atom moving with a speed of 650 meters per second? And I gave you the hint. 1 AMU is 1.66 times 10 to the negative 24 grams. All right, so what do we need? Well, we got kinetic energy is 1/2 mv squared. So that means we need a mass. Well, all they tell me is we have 1 argon atom. So you got to think all the way back to, gosh, when did we learn that? I think chapter 4 was when we talked about AMU. So you have 1 atom of argon. And so I know for a long time we've been using molar mass as grams per mole, but if you remember all the way back in chapter 4, we said that the masses are in AMU when you're talking about 1 atom instead of a whole mole. So we have 1 atom of argon, so we know 1 atom, if you look at your molar mass for argon, it's about 40. So it's going to be 40 AMU. But the problem is we can't plug AMU into this formula. Remember, for mass, I told you have to have kilograms. So how can we get there? Well, I gave you the hint that 1 AMU, so golden rule says I'll put AMU on bottom, equals 1.66 times 10 to the negative 24 grams. So that'll give me the grams, but I still have to get the kilograms. So just keep on going. Y'all know I love converting, so you know I love doing this. So we know 1,000 grams equals 1 kilogram. Or you could use your SI prefixes chart and say you know, use your 10 to the 3 grams, that's fine also. So once I multiply and divide all of that stuff that I just wrote out, I got 6.64 times 10 to the negative 26 kilograms. Okay, so after all of that, that is a mass I can actually use. Now, they gave me a speed of 650 meters per second. Those units are appropriate, so after all of that work, I'm ready to plug in. All right, so I take my kinetic energy formula, so it's 1/2 my mass, which is 6.64 times 10 to the negative 26 kilograms, times my velocity squared. So 650 meters per second squared. And so once I solved all that, I ended up getting, here, I just put my answer up here. I'm kind of out of room on the board. 1.4 times 10 to the negative 20 joules. And so that's my answer. Okay, and so you can see we have a kilogram times meters squared per second squared. Now the thing that's important is when you're putting this in the calculator, make sure you don't accidentally square the whole thing. You only want to square the 650. So what I tell some of my students, if you have trouble getting in the calculator, is just go backwards. So do 650 squared times that divided by 2 or times 1/2. And so you get a very tiny number, which makes sense because one atom is going to have a very tiny amount of energy. All right, so let's look at part B. So this time it says a mole of argon atoms moving with a speed of 650 meters per second squared. Okay, so in this case, we don't just have one anymore, we have 1 mole of them. So what do we know about a mole? Well, we know that 1 mole is, of course, 6.02 times 10 to the 23 atoms. Now, there's always more than one way you can solve a math problem. You'll hear me say that in class all the time. So I'm just going to show you one way, but there are other ways that you could do this one too. Okay, so the way that I chose to do is I started with 1 mole of argon atoms, and I followed my same process up here. But we know that when we're talking about a mole, your molar mass on the periodic table is in grams. So I said 1 mole of argon is 40 grams. So in other words, I get to skip the step of having to go from AMU to grams once it tells me a mole. All right, and so then I did 1,000 grams, of course, is 1 kilogram. And so then once I multiplied and divided for that, I got 0.04 kilograms. Okay, and so then, again, once I have my mass, I can plug into my formula. So my kinetic energy is 1/2 mv squared. So I just did 1/2 my 0.04 kilograms times my velocity, which is 650 meters per second squared. And so once I solved that, I got 8,450 joules, which makes sense because that's a lot of atoms, so the numbers should be much larger than the first one. Now again, are there other ways you could have done this one? Yes, you could have actually started with this number and just used this number to get to your moles, but the reason I did it this way was I was trying to make sure you can do it without having a part A already done. Okay, so I always like to try to just start with what I'm given, but you're more than welcome to start with this number instead and then convert from there. All right, so hopefully you got either one or both of those right. And so let's move on. All right, so the great debate is just something I do in class. It's like some demos, so we'll skip that part, obviously. So what's the difference in exothermic and endothermic? Well, thermochemistry is concerned with the flow of heat between a chemical system, which in our case is going to be the reaction, and its surroundings. A system, so let's define a couple of things before we talk about this. A system is a specific part of the universe on which you focus your attention. And the surroundings are everything else outside of the system. So like I said, for us, the system will mainly be the reaction. The surroundings will be everything else. The system and surroundings constitute the universe. Okay, so surroundings would include the air around your reaction, the beaker that the reaction is happening in, your hand if you touch the reaction, a thermometer if you put it in a reaction. Those are all surroundings. Okay, the only part of the world that's the system is your reaction. Okay, remember, system and surroundings make up the universe. So the system, like I said, is the part we focus on, which is the reaction, and the surroundings are everything else. Like I said, the beaker, our hands, a solvent, that's an example of if the solvent itself is not involved in the reaction, then it is just considered surroundings. A thermometer, etc. Okay, so system and surroundings together then make up the universe, like I just said. So what are some different systems we can have? Well, an open system is one in which matter and energy can be exchanged with the surroundings. So that would be, for example, if I had a reaction going on in an open beaker. Heat can come in and out of a beaker because it can, pass through the glass. If I boil something, steam can leave, so mass can leave. So that would be an example of open system. A closed system can exchange energy but not matter with its surroundings. So a closed system would be like, say we do a reaction in a flask that has a stopper in it. And so in that case, no matter can actually leave, but heat can still go in and out of the flask. But matter itself cannot leave if it had a cork in it or something like that. And then an isolated system does not exchange energy or matter with the surroundings. So this would be an example of a closed and insulated vessel to hold your reaction. And so heat can't come in and out or matter. So in thermochemical calculations, the direction of heat flow is always given from the point of view of the system. So a process that absorbs heat from the surroundings is endothermic, and a process that loses heat to the surroundings is called exothermic. So if heat is coming into the system, it's endothermic. If heat is exiting the system, it is called exothermic. So if we were looking at like the energy related to it, if our reactants are high energy and our products are low energy, that means it released energy, so it is exothermic. If our reactants are at low energy but our products are at high energy, that means it absorbed energy, and so it's endothermic. And we'll learn how to do these calculations throughout this chapter. So we're actually going to stop right here for the first part of it because we're about 18 slides in. And so for the rest of this section, just watch the second video for section 17.1.